So based on your discussion, it looks like you are energetic and woke up to some extent. You had enough relaxation on the weekend? It's not never enough. More. Okay, so concentrate your memories first. I'm going to ask some questions, hoping for a minimum of interactions. So, what are we doing? Yeah, that's the best answer that I have to share. And predicting future of what right now in this vicinity?
Vibration.
Vibrating molecules, yeah. You're predicting that molecules will vibrate. Yeah. And is there anything, why we are not happy with Sir Isaac Newton? Why we are not happy with just classical path approximation or assuming that all ions are point charges? What is wrong with this?
Because it's so small that it's experience quantum effect.
And which quantum effects molecules or vibrating atoms experience? Any ideas from your other classes, from maybe in-lab experience? Is there anything quantum about atoms? Not electrons, but nucleons. I'm also trying to come back and then to hope. Which experimental techniques allow to look at properties of atoms, of vibrating atoms, of their vibrational properties?
IR and MR.
Yeah. So IR. And is there any consequence of nuclear properties onto visible UV visible spectroscopy?
Yeah.
Good guess. So we will cover it partially in class, but we may want to discuss it right now. The UV visible spectroscopy is typically transitions between electronic states of molecular electronic states. But if there are, let's say, some super simple molecule where only two electronic states, occupied and unoccupied, help to generate this UV spectrum. If you do your experiment with fine resolution, you will see that there are much more features. Even if there is only one electronic transition, there will be additional features. Because each electronic level, so to say, has a substructure of sub-levels related to nuclear vibrations. And they, if you do it at high temperature, it will be just broadening. But if you cool it down, instead of having one transition, one peak in spectrum from one pair of electronic levels, you'll see resolved lines. And those will be manifestation of quantum properties of nuclei. So if your molecule is in absolute zero, right? But you can excite from ground electronic, excited electronic, and then to some sub-levels where nuclei is getting excited more and more. So this is one of the connections to real life I see. Maybe there are more. But another, so this is something one can see, what comes out of instrument. So nuclear substructure of UV with spectrum. Another thing that you already you have seen that ground state of oscillator is never absolute zero, it's a little above, so it's 0 point vibrations. There are some effects where it helps a lot. Who needs 0 point vibrations? Did any of you heard about zero vibrations? No? Okay. So nuclear degrees of freedom experience quantum features because they are light particles. And you already know from the solution of time-independent Schrodinger equation that lowest energy is not zero. So the wave function of the lowest state is not a point charge, but it is distributed. Right? So in average, position is zero, but position squared, the deviation from zero is not zero. There is some frequency, which means that there is some average vibration. So there is, I do not recall immediately some bright and impressive experiment that shows it directly, but there is a very important consequence of this zero motion. If we have so many molecules and atoms everywhere, typically we are not in a vacuum environment. Any of object that we study is either sitting on a solid substrate or is found in the solvent or in a gas phase it collides with others. And even if we are at zero temperature, the degrees of freedom which we measure on any experiment do interact with the rest of the freedom, which perform these small oscillations all the time, even at zero temperature. And due to interaction with this zero order vibrations, there is no excited state in the universe that will stay excited forever. This interaction with zero vibrations will always lead to relaxation from excited to the ground. Therefore, if you are not doing excitation, if you are not heating or kicking or irradiating by lasers, all molecules are in ground state. Because everything around performs this zero vibrations and provides a relaxation chain. Okay. Good enough to motivate heavy effort and suffering of nothing. So please, well, it would be great if you bring homeworks on Wednesday, but do not overwork, do not put all your intellectual strengths and all your precious time in it. Just dedicate some time and try to. Please prepare all your intellectual strengths to, if you organize time right now, if you are as regular people like me who does everything at last moment, prepare to have active Wednesday night, preparing slides and submitting them. No, you have also you have Thursday, right? You're submitting slides by Thursday night. Okay, then life is easy. It's enough time. This is really important thing, and as soon as we are done with our strengths of efforts we apply, will I wouldn't say it will be much easier for the rest of the course, but it will stop growing. So we are coming to a culmination. Success in this, then the rest is a little downhill. This will determine success in everything. So we already declared that our goal is to predict the future for oscillating mode. But if we prepare our molecule for the vibration degree of freedom described by harmonic oscillator in one of the eigenstates, will we get any dynamics, any non-trivial future? So I came to the same situation when everyone is frozen. Probably it's a bad formulation of the question. So before we do a reasonable discussion, there is no reason to go into it. So in the harmonic oscillator chapter, we're going to go through the same, very similar pathway as we did for particle universe. Okay? So what was the observation for the dynamics part, where we sort of weight packet, expectation value of position oscillating? How does it depend on initial condition? What was the key word for initial condition when we explored? You remember this weight packet bouncing force and value through the walls. I'm inviting you to browse through the numbers. So let me simplify the question. There are two opportunities. Suppose we know eigenstates of a quantum system. In one case, we are preparing the quantum system either in ground or excited, or second excited, and then let it go and see will it perform any motions. In other case, we are preparing superposition, like different proportions simultaneously at ground and excited. In which case, the dynamics will be more fun. More dynamics will be more dynamic. If system is in one of the eigenstates, or in case if system is in the superposition of several eigenstates.
You say non-trivial?
Non-trivial, yes.
Superposition.
Yes. So this is kind of take-home message for the whole course. If you prepare your quantum system to reside in one of the eigenstates, and you neglect interactions with substrate, so it will stay there forever. We know it is an approximation, but it will stay in our machinery, it will stay there forever. And the dynamics will include nothing but accumulation of phase, but no change of expectation value of position or momentum or some more advanced things. Right? So the dynamics for eigenstates is very boring. There is no reason to study dynamics for it. But as soon as one prepares a superposition of several excited states at the same, or several eigenstates at the same time, then there will be something interesting. And in most of the realistic systems in real life, when we perform measurements, system is brought into superposition. Otherwise, nothing will. Make sense? So this is a strategic goal for this chapter. We're not going to get it very quick. Well, you can get it very quick with computer program, where you just change potential, create non-equilibrium initial position, and then so on. but for pen and paper, it's still some mathematical work. But the goal is to prepare superposition of several eigenstates and see how it will develop in time. Make sense? So we already done this time-independent Schrodinger equation harmonic oscillator, and we did it with help of weather operators, which were a short, right? So we found that one cannot go lower than the basement. Applying annihilation operator to the ground state gets zero, and through this formulating this idea as differential equation, we found ground state. Then we applied raising operator and generated first excited, second excited. And then we split responsibility of normalizing them. So it's part of the homework. So by now, and also it's a part of a homework, but I invite you to trust that the eigenfunction that you have found match the time-independent Schrodinger equation for harmonic oscillator. So we have the solution. We already have the states. And it would be really cool to prepare initial state of a system as a 50-50 of ground and excited, or maybe 33 of ground first and second excited, and see how it will affect the change of probability distribution, the change of observables in time, if any. But we are postponing it. We're not doing it right now. It is only just some fairy tale and story to, if you're thinking about a course at your free time, then you can develop this seed of thought. If you don't, so weather triggers allow to jump up and down. The ground state is Gaussian, is normalized, and we have summarized. This one is better. We have summarized our effort in week and a half of previous exercise in the in this slide. So we have eigenstates which are converted from each other by raising operator, by and due to normalization, the application of raising operator to lower state will give the normalized next state with larger number, but multiplied by a factor, just by nature of this operator. And if you want normalized states, we do want to apply raising operator and divide by a factor which will coincide with index of the state. Okay. By the way, in this is slide from last time, and here should be +1. I found the error myself. So let's print it. Do you like this matrix? Or does it, what there are not many people in the world who may feel empathic to matrix, but what do you see, what you think about when you look at it? Well, one of the thoughts is like, break is in 30 minutes. I do not need to suffer too long. This is the summary of what we are going to get to today. So it's expected outcome of the meeting. And remember when we were just finishing the chapter of particle in the box, there was one special subject. What was the last subject before we started harmonic oscillator? What mean?
Well, like not free space, but like different sizes of boxes.
No, different. Thank you for memorizing things. Different sizes of the boxes are great, but later, after we were done with different sizes of boxes, there was one more meeting when we were trying to get rid of wave functions and formulate Schrödinger equation in discrete form, in space of expansion of wave functions in expansion over basis of eigenstate.
Density region.
No, just Schrödinger. Well, density matrix it can be also done in this basis, but Schrödinger equation in discrete representation. Does anything click? Yes? No? You don't read your notes during the night. Again and again. I wasn't reading them. So the Schrödinger equation is good. But if we are planning to do actual practical calculations, it's very hard because it deals with continuous wave functions in space. And if you are going to describe them numerically, one would need many points to discretize a function. We are doing it in the lab, but generally it is very expensive approach. So it's good for education, but not for any problem. I remember I was asking this question and Ben did answer what is basis state. So what is it? Déjà vu.
Basis set is like a approximation of coefficients. I guess.
It's not wrong. Okay, thank you. So one can represent any function as a summation. So a known function can be represented as summation of known functions with certain coefficient. And typically, if we work with particle in the box, these known functions are eigenfunctions for particle in the box. When we will be dealing with harmonic oscillator, the known functions will be set of eigenstates wave functions of harmonic oscillator. But instead of working again and again with these continuously distributed wave functions, we may just add them together and put coefficients like C sub 0, C sub 1, C sub 2 to represent how much each of the eigenstates contributes to a superposition. And if there is some dynamics, if there are some external observations, instead of writing down Schrödinger equation for wave function itself, one can write Schrödinger equation only for coefficients. So one can convert from continuous basis to discrete basis. And it is possible because of these functions are orthogonal. We didn't prove it for eigenstates of harmonic oscillator, but they are orthogonal as well. Good idea for next year. So, in case we will go onto the way of converting our consideration from continuous wave function to discrete expansion coefficients, one would need to express all operators, including Hamiltonian operator, in the space of this discrete basis. Done. Try to write down, verbalize and write down this sentence. So let's read who wrote it. Bill?
What was the question again?
So write a note after what I've told a minute ago. I'll try to no, I better let you express it and then we will refine it. Michael, did you?
My breakers.
But do you have general plan of how to verbalize it? Yet? Kevin?
Are you talking about how the eigenspace, or how these eigenspaces convert into basis?
Yes, this is correct. This is correct, but not the whole idea. Ben?
I don't have it.
But any maybe ideas how you interpret it?
Not.
Alex?
I just wrote, in order to discretize Schrodinger's equation, we need to discretize the Hamiltonian first.
Okay, so you hear each other. No one told wrong things. We just need to put together this building blocks. So we have expectations and promise that going. I cannot summarize it in one sentence myself. You better do it. I'll tell in several sentences. So we do have promise that going from continuous basis into discrete basis will be very helpful in computing things much quicker, more efficient. And if we are going into discrete basis, continuous wave functions are replaced by a set of coefficients. So that these coefficients will tell how much each of eigenfunction contributes to actual state, initial state or state out some time. And if we are practicing this idea, we need to convert each of the operators, which originally are differential operators, into matrices. So we need to convert differential operators into matrices by going from continuous to discrete basis. Okay? Is it clear or should we discuss it more? Anyone requesting more discussion? No, okay. And we are going to start from simple to more complicated. So the creation an operator in the basis of eigenstates of harmonic oscillator will look as the matrix with main diagonal is zeros and lower subdiagonal going as growing square roots of natural numbers. So if you accept it and see where it comes from, you're done. If not, I'm going to quickly go over derivations. So this all is done in order to bring our activity closer to prediction future for real systems in efficient way. You already experienced that this math is not always pleasant, not because it is someone designs it to torture people, but objectively. And one of the technical goals is to find shortcuts all the time. So this is one of the shortcuts. Whew. So here are your eigenstates, right? And eigenenergies start from one half of h bar frequency and then go by increments of h bar omega. this is our strategic goal for the rest of the chapter. We are going to represent wave function, general wave function, initial conditions, as superposition of eigenstates of harmonic oscillator that we already found with some coefficients. And then as time passes by, these expansion coefficients will accumulate phase, right? Based on our protocol to predict future. And later on, we can plug in this time-dependent wave function into protocol for computing expectation values, observable. So before this phi sub m were eigenstates of particle in the box. Now they will be eigenstates of harmonic oscillators. Gaussian, but last lecture was really successful. Everyone was showing this stuff. So those will be here. And then if we add together several of them and plug them into, they will accumulate phase, and we will be able to follow what happens in real life. I was supposed to write it down myself, otherwise it's too boring. So. Acting on the ground state, we get first state. But if we need to express first state, we can tell it as a dagger acting on the ground state, no factors. Now, if we act with raising operator, creation operator on the first state, first excited state, we are getting second state multiplied by square root of 2. Right? And if we are very picky, it comes out from normalization requirement. So, but if our goal is to get the second excited state, we write it down as I2 equals a dagger applied by 1 plus square root of 2. Right? So this is what was promised a long time ago. We are going from the first to the second. But what is the first state? What is first eigenstate? It's this one. You can plug in, right? So it will be 1 over square root of 2, a dagger, and then instead of the box, we write a dagger to phi 0, which can be interpreted as going one step up from ground state and going one step more. So just climbing 2 steps, right? So if we are applying raising operator to state phi 2, it will be square root of 3, state phi 3. So if we practice the same inversion, so we actually need phi 3. Phi 3 should be 1 over square root of 3, a dagger phi 2. But what is phi 2? This is what we defined here. So we can plug in this expression into here. So it will be 1 over square root of 3, square root of 2, and actually square root of 1, multiplied by a, dagger, applied to phi naught. A is not a defect of speech, it's just a dagger cube. So we climbed 3 times, right? 3 steps up. And because of this normalization gain, we also need to divide by appropriate factor each time. And since these factors grow up linearly, it will be that is sort of stated as square root of 1, 2, 3. If you go higher up, it will be 1, 2, 3, 4, 1, 2, 3, 4, 5. So, how do you call multiplication of 1 times 2 times 3 times n minus 1 times n?
Factorial.
Yes, excellent. Thank you. It's pleasant to be surrounded with educated people. Good. So generally, you do have procedure to generate any of the excited state by applying raising operator so many times to the ground state as which state you need, which excited state you need, right? Yeah, this is just the same thing in better calligraphy. And if you are going to state number n, you can express it as applying bigger operator n times to ground state, and then dividing it by n factorial. So we are done with one goal, but now we need to go to discrete space. We already assumed that, not assumed, we know for sure that the eigenstates are known. And we hope to get rid of this continuous function, differential operators, because we already suffered them. We were taking derivatives and integrations so many times previously. There is a way to get rid of it and deal with much shorter basis. So the main idea that you have expressed I will give up writing today, just show this. So the main idea, or maybe it's better if I write. I'm going to perform writing this equation myself and talking with this once again. So main idea that we put a lot of effort to write down that you have your own normalizations is that if you're going to discrete space, operators need to be converted into matrices. In some sense, operator converts state M into state M, if it is an operator in matrix form. Let's do connection. Just on the previous slide, we were converting ground to first excited. First excited into second, right? So operator general operator is abstract operator. Is a tool that converts eigenstate M into eigenstate N with intensity, with probability corresponding to matrix element.
The A on the left side is supposed to have a plus, it just didn't show up, correct?
Yes, it's we need a new touch. See, doesn't A. So those are bra and ket eigenstates. And if the operator is converted into a matrix, then elements of this matrix are called matrix elements. So later on, the procedure to find an observable can be cast in terms of matrix elements. So one can do all quantum theory without wave functions at all. We just need to believe in their existence and have matrix elements. Right? So we will start of finding matrix elements of the raising operator, which will be really easy, and you have seen how it looks like. And later on, we will set up matrix elements. We will represent in matrix form all operators that are needed for harmonic oscillator, like raising, lowering, position, momentum, energy, kinetic energy, potential energy. And then we will do quantum mechanics without wave functions. Right? Only in matrix expansion applications. Okay. So how do we find this matrix elements? We already know a property that A bigger acting on the operator on the statement will be equal to square root of n plus 1, n plus 1. Right? We know. Find errors for this. I hope there is no error here. So we do want to get rid of wave functions. So we multiply from the left by bra. What are we going to apply? How do we complete erasing, getting rid of wave functions? What does it mean if we see, by the way, the square root can be put from whatever it is. How do we interpret integral I sub m star I sub n plus 1 dx? And we practice the property of orthogonality, right? So that product and integration of eigenstates should give us either 1 if these two numbers are equal, or 0 if they're different, right? We already took care of it by practicing normalization. So these wave functions are normalized. If it coincides, it will be 1, for sure, guaranteed. The only little trouble that here we have n plus 1 instead of n. So we need to write that it will be 1 if m equals n plus 1, and it will be 0 if m is not equal to n plus 1. What does it mean? What can we do? So in all cases, when this equation is not satisfied, the matrix element will be 0. For most cases, it will be 0. So it will be non-zero only if m is equal n plus 1, or if n equals m minus 1. But it will be n number. By this operation, we get rid of wave functions. It will be either 0 or 1, and we can summarize it in form of delta m, comma, n plus 1. So it will be multiplied by square root of n plus 1. So in fact, we already do have matrix element. So it will be matrix. If the if it will be like mn, it will be a diagonal matrix. But if mn plus 1, it will be matrix with non-zero elements on the subdiagonal. And here are the values. Square root of n plus 1. Therefore, it starts with 2. Square root of 2, square root of 3, square root of 5, square root of 4. The summary of this meaning. You saw this matrix with subdiagonal progression starting from square root of 2. Right? Remember? I will show it in a couple of minutes as a last step. Good. Now, what if we express our creation operator as we were planning to do? Summation m. Now, instead of matrix element, whatever m, I will write delta m comma n plus 1 multiply square root n plus 1. And then, by definition of operators, here I write m n. Why I'm doing it? Because I do want to express operator not only as a matrix form, but also in direct notation with this cat and bra. So how do we process expressions when we do see summation and delta function? What do they do to each other? What sum sign does to delta function?
Does it make an integral?
It's my favorite part of the class. I can remember myself in the kindergarten. I will do something that hopefully you will remember forever. So let me redraw. So summation is a handler snake. Delta is a little rabbit that runs away. So summation is delta. Deletes. Actually, they cancel each other. If you do have summation and delta with some indices meeting each other, this construction will parse only specific elements from this progression. Parse, selects. So delta means that most of the terms in this summation will be zeros. Right? Only one will be non-zero, or whatever. Very few will be non-zero. Which ones will be non-zero? Only in case if m equals n plus 1. So we do remove summation over m, we do remove delta function, and we replace this m symbol to n plus 1. Then we do have only summation left over n, and it will be conversion from n to n plus 1 with this factor, which can be interpreted like any state number n will be converted to state n plus 1 with the factor. So this is a Dirac notation which is equivalent to matrix notation. It's just storing, writing down metrics in the algebraic form. But in this operator, and later on you will see in these notations, we do not have differentials anymore. So if we hate integrating and differentiating, we can convert into this matrix form. Okay. Experiment. So we already got it. Matrix element of equation operator is subdiagonal with square root of this stuff. Oh, we are over time. Suppose that I was writing line by line, but it is what we were expecting. So zeros in main diagonal, and here is square root of n plus 1. Okay? I borrowed 2 minutes from your time to return some bucks. Meeting is done. Looking forward to see you on Wednesday.
It's pretty cute.
Growing on you?
Yeah.
The hedgehog's
Like,
growing on you? Is it pretty nocturnal? Or?
She was, this morning she was pretty active. Last night she was super active.